Hi everyone. What I'm going to talk about is how to evaluate uh, or how to use step response of a system. So you have a given system H, and how to use the step response of the system in order to evaluate response to another input, which can be represented nicely as a combination of shifted and scaled step functions. Unit step functions. So let's look at the problem. So the problem is you have some signal xt, right? And as we know, in order to recover the output yt for a linear time invariant system, what you do is yt is a convolution of xt and the impulse response of ht. This is true for any input. In particular, if xt is delta t, what do you think yt is going to be? Well, it's the convolution of delta function with ht, and if we evaluate that convolution, it will actually turn out that y of t is h of t, and that's not surprising because if you give an impulse as the input to a particular system, you should get the output as the impulse response, so that makes sense. Similarly, if you put xt equals st, or sorry, ut, where u is the unit step function, then what will yt be? Well, yt turns out to be, as up here, it's the integral, or first let's write it as a convolution. It's st convolve with ht. And what is that? So that is equal to integral from minus infinity to infinity. St is u of tau, but let me, because of the commutativity of convolution, let me write it as u of t minus tau times h tau d tau, right? Which is equal to this step function is non-zero only for values of tau which are less than t. So this goes from minus infinity to t h tau d tau, and this is something we discuss in the class. This is really a running integral of the impulse response. So what I want to do is I want to use the step response. I'm sorry, this is not st, this is ut, and yt for an input ut is denoted by st. St is really the system h with input ut, and that's what we calculated here. So the question is, how do we use st to evaluate responses of some interesting functions? So responses to some interesting inputs. So to consider an example, let's take, let's actually, I want to go to a new page. Let me figure this out, how to go back to a new page. Okay. Okay, so let's consider an example. Xt is equal to ut minus 1 minus ut minus 2. Okay, now what is this function going to, so this is my input, and my impulse response for the system is given by e to the power minus t times ut. Okay, let's plot these to understand what these are. So xt is ut minus 1 minus ut minus 2. So if I plot this, xt, ut minus 1 starts at t equals 1 and goes up to 1 and then keeps going to infinity, but you're subtracting ut minus 2 here, so you're bringing it back to 0. at 2. Okay, so that's my xt. What is my ht? The impulse response of the system. Ht is e to the power minus t ut, which means it's 0 for t less than 0. So here the value is 0. And after that it's e to the power minus t. Okay, so looks simple enough, and of course you can evaluate this using simple convolution. So you could just do yt equals xt convolve with ht, and that will give you the answer actually, and it's not a very hard integration to do. But what we want to do here is to use st, the step response, in order to understand what the output of this particular xt is going to be. So remember, st is ut convolve with ht, right? Okay, so the way to do this is the second approach. So this is sort of the first approach, and we want to use st, right? That's the second approach that we want to try. And in order to do this, it's good to notice that the input xt is actually a difference of two unit step functions. So I can write effectively yt as ut minus 1 minus ut minus 2, which is just xt, convolve with ht. So now remember, convolution distributes. So this is ut minus 1 times ht, oh sorry, convolve with ht, minus ut minus 2 convolve with ht. Okay, so what we can do is we can evaluate these two quantities separately, clearly, right? But the interesting thing here is that this is just a shifted input, a delayed input being put into a linear time invariant system. So the output is going to be delayed by the same amount, right? That's the property of time invariance. In a similar way, when ut minus 2 is put, it's also an output. The output will be delayed by two time steps, or 2 units of time, and will also be scaled by -1 here because of the linearity property. And then we can just add the output. That's effectively what's going on. So let's evaluate so to evaluate these two quantities, what we can do is we can first evaluate st, which is our step response. So what is st? As noted before, it's integral from -infinity to t, h of tau d tau, right? And what is that h of tau? It's this, so which is equal to integral from -infinity to t, e to the power minus t times ut, or rather, sorry, e to the power minus tau u tau d tau, right? What is this? So u tau is 0 for all values of tau that are less than 0. So this is integral from 0 to t, because the product of these two will also be 0 for those values. So it's just integral from 0 to t e to the power minus tau d tau. But when does this hold? This is true only if your value t is greater than 0. But if t is less than 0, then this integral is also 0, because you're essentially integrating just 0. So it's 0 if t is less than or equal to 0. Okay, so what is this integration? Well, if you compute it, this is simply 1 minus e to the power minus t. So this is equal to 1 minus e to the power minus t. The st is equal to 1 minus e to the power minus t if t is greater than 0, and 0 if t is less than or equal to 0, right? Which succinctly, and just check this mentally in 5 seconds, this is equal to 1 minus e to the power minus t times ut. The succinct representation is useful because now you don't need to remember to shift the output by a constant. That will just show up in this u of t itself when you have to evaluate st minus 1 and st minus 2. Okay, So going back up here, you had to evaluate ut minus 1 convolved with ht and ut minus 2 convolved with ht. This quantity is simply, let me change the color. This quantity is simply st minus 1 for the reasons that we discussed. And this quantity, this whole convolution is simply st minus 2. So what we're trying to evaluate, this whole thing is st minus 1 minus st minus 2. And we already have st here, right? So all we need to do is shift and subtract. So let's do that on the next page. So our yt, which is the output, is given by st minus 1 minus st minus 2, which is equal to, because st, remember, is 1 minus e to the power minus t times ut, it's simply 1 minus e to the power minus t minus 1. I replace every t here by t minus 1 times u of t minus 1 minus 1 minus e to the power minus t minus 2 times u t minus 2. Okay. So this is really your output. You can plot this. It's not very hard to plot. The output looks like this is yt against t. You start at 1, you keep going up, and this is really the first exponential, which will eventually begin to converge. But before even it converges, you get a decrease starting at 2, which is where the second exponential takes over, and asymptotically it goes to 0. Okay, so that's the example.